Loud. Good evening and good morning to everyone, depending on where you are. Uh, um, Rich is offline because he's got a storm going through and has lost mains power and managed to get this going from his battery, but his battery power is limited. So I'm the host. Um, so let's see how we go with Drake's Lounge Australia. And just for background, as we were just saying before the recording started, uh, temperatures in Victoria and certainly in Melbourne are crazy hot. So if we disappear in a cloud of smoke, you know why. Looking at my iPad here, the forecast for today is 40 Celsius as a maximum, which I think is around about 104. Someone might tell me that. And then coming up, well, so tomorrow's cooler, Monday is up to 30, and then Tuesday is forecast to be 43 in Melbourne, which is, I don't know, someone will convert it for me. Further up north in the States, places like Mildura and Echuca, they're getting 45. And it's just crazy.
That's about 112, I think, 45.
112, right.
Something like that.
It's all pretty crazy. And certainly here in Melbourne, we've had no rain for quite a while now. Gardens are not looking very good. So it's all a bit of a challenge, really. We did, however, have some good aurora the other night. Steve, I don't know, Tim, I don't know whether you saw the aurora.
I've got the video to show if you're interested in that.
Right.
Were you going to do that?
We'll have a look at that.
Tim, that one.
Yeah, I've got that. I've got that in the presentation that I've got for the
Yeah.
Well, I won't steal your thunder. You can take care of that.
Yeah,
we'll dramatic
we'll come to that.
Very beautiful.
Yep. All right. So yeah, that's I missed the warning on that one, so I could have gone out and apparently the car parks along the south-facing coast along near in Melbourne and around were absolutely jam-packed. The police had to go out and direct traffic because so many people were there. But it spread quite a long way north into New South Wales, I believe. So for our US friends, that's the equivalent of extending a long way south. And they were quite dramatic. So
was it seen in the US? Was it seen overseas?
Some, yeah, I think there was some.
Dennis said yes.
Dennis is saying yes. So yeah.
I don't know. In the U.S., you're talking about the Aurora.
Yeah.
Yeah, we had some. We had some last night or night before last.
Yep.
Here in Montana.
Yeah. So from me, my report is only that I'm working on yet again a conference paper for our physics education group, Vic Physics. That's coming up at the end of February. Mid-February, February the 20th, I think, something like that. And that's about space weather, which is very topical, given the aurora. And the biggest single thing is to get across just what an active bit of space we actually live in, where the Earth is located. The textbooks tend to be very blasé about the Earth and space. Space is empty, there's nothing happening, which is, of course, totally wrong. There's a lot happening, and given our proximity to the sun, there's a lot happening which has significant effect on radio communications, satellites, and so on and so on. So I might be able to do a summary of that paper for the journal at some point, but as I say, I'm still working on that, coming up in February, the middle of February. I'm also working on a series of sessions for teachers who don't have any physics background. So as a science teacher, if you're chemistry trained or biology trained, you still have to teach physics in years 7 to 10. We have an awful lot of teachers in schools who have no physics whatsoever and therefore teach the physics not so well, let's say. And so we're developing a series of courses for them. And I'm doing the Earth and Space one at the moment for presentation later in the year. There's a ton of resources out on the internet. So I've got to condense those into, it'll be 2 days to cover the whole of year 5 to year 10. So that's keeping me well and truly busy. Now, I'm not quite sure. Well, Steve's got something and Tim's got something. Steve, do you want to kick off and then we'll follow
Well,
with
no,
Tim?
I think I don't have anything specific.
Oh, right, okay.
I'll just make the comment that we spent a lot of time since our last SARA session to get our dish up and running again. Mechanically, it's been fine, but we had issues with the receiver, and then a remote access, the communication link between the internet and the system up at our country property, that failed. So it took a while to get that fixed, but that's all running now. And we've been using the dish for quite a bit. And Tim mainly has done some amazing things. So I won't present anything myself. I'll hand it over to Tim, and he's got quite a few things to wow you with. Go ahead, Tim.
Okay, thanks, Steve. So I've got two things I want to talk about. One will be the work from the ASV, and also I'd like to just talk a little bit about my backyard telescope, which I built. I've just got a couple of slides on that. So I've put it all into I had lots of bits of information, so I put it into a presentation, and I'll see if I can get that running.
You should be right for sharing. I've got the thing right here.
All right, if I get that, and then I'll do that. Is that working? Can you see all that?
Yep, I've got all that. Yep.
So just to remind you, this is the telescope up at Heathcote, which I've been playing with. The nice thing, as Steve said, that we can run it from our home, comfort of home in Melbourne. Saves a 2-hour drive up to the site, and it's been working really well, and we get some nice results. But the first thing I want to show you is that John Kay, who's a member of the Astronomical Society of Victoria, I'm not sure what sort of camera he used, but he set this up to take a video of the Aurora. And this is the one that Steve was mentioning is pretty good. And I'll just show this. It's really, really nice. Hopefully the soundtrack comes through.
No, there's no sound, Tim. You didn't share the sound.
Okay, let me go back then.
So it's in the share screen. When you go to share screen, share sound as well.
Yeah. Okay.
You have to unshare first and then share again after you check.
Okay. All right.
Take the video off. Yep. Go back. Yep.
So where's the?
So you go share screen, and then click. Then on that pane, when you've got the share screen, there's a button down, share options.
Oh, share sound. There you go.
Yep.
I've got it. Yeah.
Right. There you go.
And now I've got to find the presentation.
Find your file.
It's gone off screen. Hang on. Let me.
Yeah, you have that open on your desktop as well.
Worth saying while you're getting organised. Worth saying, Tim, we can't access the Dark Sky site when there's particularly these days like today, there's a total fire ban, and no members are allowed anywhere near our site. It's just too dangerous. It's right in the middle of a forest, of bush, and anything could happen. We hope it won't, but that's the benefit of remote access. We can do it from home. And it's also worth pointing out in this video that you can see the Magellanic Cloud. That's the large one, I think, which you can't see from Northern Hemisphere. All right, away you go, Tim.
Okay. So it just so happened that as he was taking the video, it was around about midnight. I thought, I could do a scan of the Southern Cross and the Milky Way. So I set the telescope running. So I got this nice video of the telescope.
See
It was to the surprise of the guys who were taking the astrophotography, though, because they
Yes.
weren't expecting it. They always like to have something in the foreground, and our dish is something of a bit of a prize. So they do that. They set up their cameras and often get that in the foreground, but they
And then
weren't
it
aware of the
moves.
fact it was going to move. That's right.
That's right.
That was
But I think-
fantastic
I think it looks
serendipity.
great. It looks
Yeah.
good, actually, seeing it doing a
Worth
scan.
saying, you can see the coal sack there right in the middle of the screen.
Yeah.
Tim, you could probably put your cursor onto it.
Can you see
Yeah.
my cursor, or do I have to move something else?
Yeah, we can. You can see
Okay,
the
so,
pointers. You see the two pointers
So there's
pointing
the
upwards.
Southern Cross there,
That's the Southern Cross, yeah.
and that's
And
the
that's the
coal
coal
sack.
sack.
That's the head of the emu.
And that's the rising emu. You can actually see the emu quite well there.
I
It's a
think
bit
that's its
washed
body.
out because of the
That's
Aurora,
its leg.
unfortunately.
Yeah,
Yeah.
but it is
Got a
it's
head,
showing
it's
the
got a
emu.
beak. Yeah.
Yep. Emu rising. It's very significant for our indigenous friends. That's the time to go and find the eggs and eat them, I'm told.
Yeah.
They managed to survive 40,000 years here, didn't they? So
At
they used
least.
the stars for all sorts of purposes.
Yeah. First astronomers.
Yep.
Okay, so I'll just give a little bit of background as to what I did. Is I did a couple of scans over January 17 and 18, so it was fairly recent. And just to show you this shows the chart of where it's scanned. This is Scorpius, so it was in this region here. And the way the software is configured is we can set up a grid of points and tell the thing to go, and then it'll just scan all over those points and collect data for each one. So that was the first scan on the 17th, and this was the one on the 18th. And these two were combined together, and I had to eliminate some of the overlaps because it was causing artifacts in the way I was generating images, which I'll show you in a moment. So I have to think about exactly how to deal with that a bit more thoroughly. So what happens is the software-defined radio that we have, it outputs obviously the radio signals, which I then Fourier transform, and then you take the modular square of that, and that gives you essentially Doppler spectra. And an example is shown below, and you can see this is exactly the point where I took this from. And so that you can convert the frequency difference from 1.4 gigahertz into a Doppler shift. I mean, you guys all know this anyway. So this just shows essentially the hydrogen signal. There's a temperature scale there, which I think is roughly right. We did a lot of work trying to calibrate the whole system. Steve climbed up onto the scaffold up to the dish and injected a radio signal into the low noise amplifier, which we could then look at what was coming out of the software-defined radio back in the what we call the lab. And from that can get a calibration. But there's a few other things that had to go into this, which was the size of the dish, the effective solid angle that it's collecting from, and also the efficiency of the feed horn. Some of those things aren't that well calibrated. So I think this is a reasonable ballpark figures. I don't know if you can actually read the numbers there, but they're in velocities down the bottom in kilometers per second. And then
The peak is about 110. Is that right, Tim?
yeah, and it's sitting on quite a large background. So that was the other thing, is there is a background level there, and that's quite, I'll point that out, but that's relevant as well. So just another example, this is from another spot, and you can see the background level's gone up, and we're getting more complex Doppler signals. So the Doppler signal is due to the main peaks are due to the hydrogen, because we're looking at the 21 centimeter line. This was a really interesting spot, and you notice that the peak has a really large dip in it, which I'm pretty sure is an absorption peak. So this is evidence of self-absorption, which says that there's a cold or a cool hydrogen cloud between us and whatever it was that I was picking up in the background there, which is around about the center of the galaxy. And that's been absorbing some of that radiation. You can see again the background level shifts up and down. So the next thing is to then create some images. So this image was from that scan region. And what I do to get this, I'm interested in just the hydrogen signals. So the aim is to then subtract off the background. So I fit a line through the background, which is fairly flat, and then just plot the difference from that background to the peak for each sample point. And in this plot, the average, it's an average measurement. So I've integrated from minus 50 kilometers a second to 100 kilometers per second at each grid point to generate an image of the radio emission. And there's this mathematical technique called a polyharmonic spline, which enables you to interpolate between a random set of samples. So this image data is the interpolation. And just to orient you, there's the tail of Scorpius, and that dashed line is where the data were collected. So you can see that the actual image I've printed goes beyond that, and you can see how it sort of fades off at the edges. So anything outside that boundary is not really all that probably useful. And there's also, if you look carefully, there's a bit of a line artifact in the middle where the two data sets were joined. I had a discussion with Steve about that, and we thought it could be slight shifts in the calibration between scans. So that's something we need to look at. But anyway, so it produces quite a nice image. The other one that we did is, now the background signal, which I've shown here again, is due to just the electronic noise in the system, but it's also due to the broadband radiation that comes from the sky. So instead of plotting the hydrogen peak, if I just plot that background signal and scale it relative to whatever the minimum is, then creating an image of the offset at each point gives the broadband radiation. So this is not the hydrogen signal. This would be something like synchrotron radiation and whatever. And the nice thing is we're getting a really hot spot right near the center of the galaxy, which I thought was interesting. There are a few artifacts just to the, in fact, if you can see my cursor, can I do it? No, it's gone off, doesn't matter. Just to the right and up of that central spot, there's another patch, which I think is an artifact. What we do is from time to time, there's noise signals that come in. There's sharp pulses from just radio interference, and I think some of those cause shifts in the offset, and I think that's just a noise signal, that one. So that's all really fascinating. I found that really interesting. So the other thing which I thought was interesting was I was fascinated by this absorption peak, and I thought, well, we've got all this data. All of these hydrogen signals change according to the Doppler shift, and I was wondering how best to actually plot that. So so what I was thinking was I could create a sequence of images using the Doppler shift. So in this case, it was from minus 50 kilometers a second to 100 kilometers a second. And so each image was created in 2 kilometer per second steps. So I ended up with, 75 images. And then I combined that into a movie as a function of Doppler shift. And that actually I find really interesting, fascinating. So if I start this, hopefully you can see at the top is the actual velocity. So this is scanning through the velocity from that data set, just measuring the hydrogen signal. And what I find interesting, okay, sort of fades off now. But what's really interesting is around about 18 kilometers per second, I'll just scan back there. You can see, oh, there's that little dot that pops up there. That's a noise spike. That's interference. But if I just scroll back here, you can see as you go through there, you can see almost like that dark band here that goes across. So that's the absorption line. That's associated with that self-absorption. So that's representative of the distribution of some cold gas cloud. Which I found that was fascinating. So there is something there. I'll just run that again. I'll find that.
It's mesmerizing, Tim. Your cursor does show up on this one too.
I'm just trying to see if I can run the thing again. Actually, if I go back and run it forwards. Yeah, there we go.
Tim's used a color palette called Magma, was it?
This one's Magma. This is my favorite. Steve prefers a nice traditional spectral color, but The romantic in me likes this.
Well, it does look very galactic, doesn't it? Like a
It
glowing
does. It almost looks like
gas.
it's real. I mean, it's not.
Yeah,
So
yeah,
yes.
yeah.
So that's
I wonder,
all I want to present about the ASV stuff. If anyone wants to have comment about
could
that.
we ask the other experts if they have a theory about this absorption line? Is it real? Is it something that we would expect to see? Is there another
We've seen it
explanation?
too.
Yep.
We had a STEM student kind of try to map it and found that it wasn't centered on the galactic center, which we thought was kind of fun, that it was kind of off to the side. So, okay, cool. Yeah, some big clouds in the way.
So it is real. It is an absorption cloud.
Well, this other amateur says that we saw it too, and we could draw a line around it, I guess. I'm going to try to
Okay.
find the poster and post it here.
It is real because I've looked up some papers on it, and I've got one from a group that did a big survey of hydrogen in the center of the galaxy using the Arecibo radio telescope. So this is the big stuff, and they were pointing out all the absorption lines. So yeah, I'm pretty sure that's self-absorption. In fact, a lot of the little dips you see are due to self-absorption, they claim. So yeah.
So neutral hydrogen clouds don't all just radiate. They
Well, they
do
have to be
absorb as well.
excited somehow. Yeah.
Somebody
In fact,
got in the way, yeah. The other point was you were scanning through the different velocities, and the Planck, I don't know, Observatory, Planck Foundation or something like that, also made a movie. So I'll try to put that link in the chat as well.
Oh, good. Okay. Yep.
And it
There
looks
was.
just like yours, yeah.
Oh, great. Okay. Yeah, it's hard to. It's this in astronomy. There's so much stuff around. It's sort of hard to find what little bits of information. So much. All right. So I'll just move on. So the other thing I did was, as you know, the ASV radio telescope was out of action for quite a few years, and it basically broke the day I joined. So I got a bit angsty about it and thought, well, maybe I can build my own radio telescope. So I'll just briefly talk about my backyard one. I don't have a good picture of it because I've pulled it apart again because I'm redoing the motor drives. But you can see this is actually the view where I'm on that computer at the moment, and I get a view out the side window, and that's where it was. It's 1.8 meter dish with a little feed horn up there, which was basically made out of some plumber's pipe with alfoil wrapped around the inside, and it has a little monopole antenna stuck in the middle. Pretty traditional sort of thing.
I did some testing on that feed horn of Tim's, and it's quite resonant and quite good quality, as it turns out. We used a network analyzer to verify that.
Actually, I rebuilt it, Steve. This is a slightly different one.
Oh, okay, but it's the same principles, though, Tim.
Yeah, it's the same principle.
It worked out quite well.
This had a slightly smaller diameter, which actually makes it a little bit more resonant. Because that other one, I was getting a signal, but it wasn't very good, so I rebuilt things. If you remember, I also had a central pole up the middle of the telescope with that on it, and I think that had some problems as well. So I've gone to the three, the three struts thing.
Yep.
So basically, just the electronics. I bought this. These were mini circuits, which I bought offline. So it has a couple of amplifiers in it, and also I thought, well, I should probably put in a filter, because there's a lot of. I'm in a suburb of Melbourne, so there's a lot of noise. In fact, I can tell when the postman is coming around on his motorbike because I get a whole lot of hash coming through on the system. Anyway, so that put the filter in to try and eliminate a little bit of that. So this was the signal that I get. It's obviously, this is not corrected for anything. So there's a lot of frequency variation in the, not only in the low noise amplifiers, but the whole system and the software defined radio. So the way I was calibrating this is pretty standard, I guess, is just to point the telescope at a cold part of the sky and then get a scan. and then pointed at the object of interest, and then used the two to iron out the frequency variations. I'll just show this last one, which was, I pointed it at the small Magellanic Cloud, and I was very pleased to be able to pick that up. So there's the central peak just at about minus 20 kilometers a second, which is hydrogen. And then at around about minus 180 kilometers a second, there's this broad peak there, which is the small Magellanic Cloud. And I know that because we've used the ASV telescope to map that. In fact, I think I presented a bit of that last time. And that's exactly where that peak is. So that was quite pleasing. But at the moment, I wasn't very happy with the motor drive system I was using. These were dissect motors. So these are motors used to control the position of dishes for picking up satellite TV. And I got them really cheap. They were being sold for 20 bucks, actually a little bit under 20 bucks. So that's why I got those. But they were a bit crude for what I wanted. So that's why I'm rebuilding it. I'm just fixing that up. So that's me done.
Well done,
Excellent,
Tim.
Tim.
Excellent. Amazing stuff. Really,
That's only
really.
about, that's a 1.8 or 2 meter dish, Tim.
1.8, I think it is. Yeah.
So, given how well that system is now performing, are we, Tim or Steve, is there any further communication with Parks because they were interested in our data at some point?
Oh, I'm sure they are. We haven't finished using it ourselves yet.
Right.
Look,
Yeah,
Not
we
guys,
getting
I'll be
anywhere
honest.
near it.
You know, if we were to hand this over to the professionals, we'd never get a chance to use it ourselves.
No, Steve, you don't do that. You don't hand it over to the professional. You keep the login details to yourself.
Look, it's always a question of our availability, time, constraints of us using it ourselves, learning how to use it. Tim has been the pioneer in many respects. He's had the bold courage to run a scan, as you saw in the Aurora video, run that scan overnight while he's in bed. And I've always sat here looking at the thing, capture every sample. But Tim has been running very large arrays of scan areas now, and they take something like 5 hours, was it, Tim, to complete the full scan?
Yeah, in the code, remember we set it up so that it gives an estimate of the scan time. It was over 3 hours, but I think that because I think those ones were like about 3.5 hours. But then that one which we saw on the video of the Aurora, that took a lot longer because if you saw it was getting up near the zenith and it had to keep spinning around in azimuth to try and pick up those, and that actually took a lot longer, that one. But
Yeah,
that was
mechanically
the
the azimuth change is quite quick. You could see that in the video too. So because the video sped up, of course, but the altitude changes, the jacking screw was very slow. And you were moving it across a wide range of altitude, weren't you?
Yeah, it was. And again, I tried to set the software up so that it would scan in azimuth first and then just do little serpentine steps in elevation, but it wasn't doing that. So I'll have to look at the code and see where that generally
That may
it
have been,
does. But in that particular one,
of the zenith.
yeah, I'm not sure. I'll have to check that. The problem is if you're doing a scan that's roughly at 45 degrees, which one do you scan first? So yeah. So it has to flip which one it does anyway. Yeah.
I'm still on the mindset that we need to continue to do some further calibration. There's evidence that the telescope's not pointing at the right direction. We've done studies of objects like the sun even and scanned across the sun, and there's asymmetry about the location of where the sun is. So there's pointing errors that we want to try and correct, and that's adjustments in the motor drive system. We have to get Phil Costigan, our section director, to help us out with that. I still think there's potential calibration errors in the amplitude measurement, and something we've never done was to just have the telescope point at one single point in the sky, get a reference level of that point, and then track it for the whole day to see if there's any change in the level of that signal. And that would be a revealing test. Hasn't been done yet. A few other tests as well. But we're very close to getting some fantastic results. And even in that aggregate presentation that Tim's done, it's been remarkable. and discoveries are being made that we weren't aware of. So it's a fantastic learning process. And there's obviously the whole area of the sky to study, and we haven't done that yet. Capture more and more samples, build up a bigger picture to have the full Mercator projection of the whole sky, southern sky, in one picture. That'd be great.
I suspect that some of our US friends are hoping some data might come their way as well to fill in some of the gaps.
Well, I was just asking, what is the data format in now? What kind of files are you recording to?
So these are binary files, and what it outputs is the Steve put a lot of effort into monitoring the cabinet up on the end of the dish in terms of temperature and humidity and temperature in a number of places. So all that data gets stored in a little data file along with the essentially the uncalibrated power spectrum. So for each sample, you get a little block of information at each, and it also stores the right ascension declination it thinks it's pointing at and the elevation azimuth. I've written a little Python script that can pull the data out, or I'm happy to send it. It's actually a C structure. So if you've done any encoding in C programming language, it's just a C structure. I'm happy to share that if anyone wants it.
Well, I raise my hand. That sounds great. I'd love to see if I can convert it to a format I'm more familiar with. That'd be great.
Sure. Yeah.
Tim, I sent you an email.
Yeah, put your email in the chat, and I'll send you some stuff.
Yep.
I just had a quick comment. I think your overlap is the radio equivalent of a Moiré pattern, isn't it? In visual stuff, I know that the Moiré pattern is due to overlapping, separate overlapping pictures of the same thing, so to speak.
Yeah, that's a good point. So there's a thing called, as I said, called a polyharmonic spline, and what it does is it's essentially a method for interpolating between points. So you just basically dump all the points into this matrix, you invert it, and then you can then specify any. So in 2 dimensions, you can specify any coordinate, and it'll give you the interpolated value. And in the overlap region, yeah, there was it wasn't all that stable, and I'm not sure if that was due to, maybe it was a Moiré, or I'm beginning to think maybe it was just the noise offset in the system was a bit different from point to point, so you tended to get oscillations as you jump between them, and so you'd see this pattern appearing.
Yeah,
so
could be.
Possibly that was the thing.
Sort of a wavy pattern.
Well,
Stripes?
the points don't perfectly overlap, so that even though the spacing is the same, there's sort of different angles, and so you get this weird, almost slightly random.
Yeah, the Moiré pattern would be where the overlaps would be some kind of regular beat. So sort of like the equivalent of a beat frequency, really, in a spatial sense. So that you would see repetitive bands across the overlap pattern. That's what it would essentially be like.
Yeah, I'd have to, anyway, it's something I need to look into. I was just doing it quickly just to get so I just wrote something to eliminate the overlap points between, well, actually didn't eliminate it. It got rid of them out of one of the data sets. But it's certainly something it needs looking into.
It's good
Paul,
anyway.
Put his hand up.
It's really spectacular, though.
Tom, do you have a question?
Yes, I wanted to ask him a question about his C output. Are you outputting that information in counts, or have you calibrated it to temperatures or dBs or something like that? What is that?
Yeah, so this was the problem, is that there was no information. So it's a SDR Play RSPDX software defined radio. Oh, in fact, I've got one here. It was one of these. So we got one of those up at the dish. I don't know if you can see that. And there was no information to say. Basically, you're getting you're getting a digital number that comes out, and there was no information to say how that related to what came in. There was no calibration. It would tell you the gain it was using, but that's useless because you don't know what the full scale range of the analog to digital converter was. So that was part of the problem. So what comes out is that those numbers get Fourier transformed. So there's quite a bit of processing there. And then there's a mod square of that, and then there's a couple of other factors that try to eliminate the dependence of that number on sampling frequency or sampling rate, so that the number should be independent of the sampling rate. So you get that as a sort of a floating point number, or you get 1,024 of them, and then you then have to come up with a calibration factor. So we've got some numbers that we think are reasonable calibration factors, but we're not entirely sure how accurate they are. So I can give you those numbers as well.
Well, yeah, if someone's going to try to make use of their data, they need to know whether it's coming out in counts, which is what it sounds like, that it's just giving you the count value of the A to D converter and putting that in the file. And
no, it's not the counts from the A to D converter. It's a Fourier transformed number, so that it's a floating point number. And it's also there's a large number of averages. So for example, if we do a 10-second integration, then there's 20,000 or so of these things that get averaged together.
okay.
So
Okay.
yeah, so as I said, I can give what we think are the calibration factors for our telescope to convert it to a brightness temperature, or Jansky's or whatever. But as I said, it's not clear exactly how accurate they are. They look reasonable ballpark figures. The numbers are coming out similar to what you'd expect for the brightness temperature around the Milky Way. So I think they're not too bad, but there could be a factor of 2 error in our calibration. I'm not sure.
Okay. Thank you very much. That indicates that there really is a lot of uncertainty here about just exactly what your data is.
That's right. So in terms of relative power, it's accurate.
Yeah.
Because we know the gain of the software defined radio. You can change the gain of that, so that's all embedded into it. But then there's an overall scale factor for all of it that's missing. The other thing that we do also is we got this noise source that we turn on, and so whenever I do a scan, I start off by measuring the noise in the system, and I save that as a file, usually at the beginning, so that we can calibrate out the gain variations with frequency. So in my backyard telescope, I showed you a picture of the gain variation with frequency. It varies quite strongly. And we have a similar sort of pattern with the the data from the dish, or from our radio, the ASV radio telescope. So you do have to scale it, and so I normally use the noise variation and scale it by an effective ratio relative to the center line of the signal.
Okay. It's going to be a lot of work there to try to make sense of it, but
Work to be done, I think. Yeah,
it is.
work,
It's
work in progress.
It's not trivial. That's certainly true.
Yeah, but you've come a long way, Tim and Steve. I think it's all looking very positive, given where we were, while the dish was out of action. It's come a long way.
I was just going to quickly share a live screen. So that's the telescope operating now up at Heathcote. It's the telescope's been left in a sort of a parked position. It's not tracking anything, is it, Tim?
No,
would have been the last to use it.
Not. Yeah.
So
I'm
it's
getting
near
close.
the Southern Cross, is that right? Or near Orion? What have we got there? Zoom in a bit. Rigel Centaurus.
Yeah,
Well,
well,
that's
that's the
one of
pointers.
yeah, that's near the pointers. So that where the red circle is where the telescope's pointing, and on the right hand side is the spectral display. It's doing a regular update every 15 seconds, I suppose, and doing the integration stage, which is you'll see it flash at the beginning. It just did it then, and then it sort of settles down. There it goes. So it grabs a capture, and then it does this integration. You can explain that better, Tim.
Yeah, so basically it takes 1,000. I think this is currently what are we? Yeah, it's 4 mega samples per second. So it takes 1,024 of those, does a Fourier transform, and then converts that to an effective power. So it's essentially a mod square. And then it grabs the next one, the next 1,024, and adds it to the previous one, or averages it with the previous one. Well, actually adds it, because you really only average at the end, and this is sort of the display is showing a sort of an intermediate step.
And below it is the waterfall display. And I prefer to use the spectral mode, and I've made adjustments on the screen to get that background dark blue as the background level, and the peaks appear as a bright spectral color, which can go all the way up to sort of a rainbow of colors to the higher intensities. Tim preferred this other mode for various things, that magma mode.
Oh, actually, Ember on this one. The magma is on
Ember?
my computer. Yeah, I haven't.
You
I've
prefer
redone-
Ember on the waterfall?
No, the reason I prefer Ember on this one is because I rejigged the magma scaling. So on my home computer it's fixed, but it's not on that one.
Okay. Yeah, so we got quite a few features.
Whatever.
Tim's been
Yeah.
upgrading the software regularly, haven't you, Tim? And it's we're even upgrading some of the software remotely. Is that right?
Not really remotely. No, it's a bit
Okay.
awkward actually. I can do a little bit, like I fixed up some of the gain numbers because I can just type those into a file. But to do any main editing is a real nuisance over the VNC. It's a bit sluggish.
Oh,
And
yes.
unfortunately, we can't download. We
It's
can't
still not ready.
we can't transfer files from our home
Lee
computer
still hasn't
up
sorted
to
that
the
out.
site. No,
Okay.
we still don't have access to do that. We can do it the
These-
other way. So I can download data from the system.
I'll just quickly switch across from that screen to another screen, which is this one. So this is another desktop computer up in our laboratory up there. And it's showing the status monitor, my toy, which is looking at all the environmental conditions of the receiver. So voltage, current, we've talked about this before. Currently, the ambient temperature up there is only 26.7, but later this afternoon, that's going to get it well over 40.
They get, yeah, much higher.
But the Peltier cells are working quite well, even at this temperature. It got a look. What's that? 8 p.m. yesterday. That's 8 p.m. yesterday. It got to over 32 degrees. The low noise amplifier is hovering around 15, and that's been pretty stable for long periods. But the larger enclosure, which probably doesn't have a powerful enough Peltier cell on it, we're constrained by the power current rating of the power supply. The front end box starts to break loose in its temperature stability when it gets over 30 degrees. I'll quickly stop sharing that and share another image, just briefly. This one, yeah, that's a static image. That's the one I want to show. Oops. Where are we now? Zoom, back to Zoom. Share screen. This one. So this is a static image, and here the ambient temperature early in January the 7th, it got to 44 degrees at Heathcote, and it went off the chart on the cabinet temperature.
Scale.
Yep. And you can see that the low noise amp went from its normal 15 degrees up to about 20. So that's still not totally useless, but the front end went from its 15 degrees up to 30 degrees. So we have to be aware of those temperature variations, because I've shown charts previously where we know the gain of the receiver is changing with temperature. So we're doing our best to try and create a stable temperature. But as Tim's mentioned, every time we take a measurement, we're grabbing all of those environmental figures. So there are ways of retrospectively calibrating the effective temperature anyway.
Very good. At least it's staying pretty stable, even in those extreme conditions. That's very, very good. And Steve, your mention of Peltier cooling, some may remember my reference to a muon detector, which is being developed by Swinburne University. And I borrowed one for a while and did some tracking. And we were looking at acquiring one for the Astronomical Society, but the cost is quite high. And another member suggested a cloud chamber might be an alternative. Now, in fact, muons were originally detected by a cloud chamber, but a very sophisticated one. So that sent me off looking at various cloud chambers, and there are a whole range of different models. Some of them use dry ice. So the idea is you use isopropyl alcohol, you warm it up a little bit so it vaporizes, and then you significantly cool it using dry ice, for example. And then so it supersaturates. And then when the charged particle comes through, it leaves a vapor trail. And the problem is getting hold of dry ice nowadays, particularly for a school where you only need a small amount just for the demonstration. So then I was looking at alternative cooling methods. One of them is a syringe, which you pull and that drops the pressure inside the chamber, and that supersaturates the vapor. One is to use the gel pack that you'd put on an injured muscle of some sort, usually freeze it. So you put that into a heat sink, just a normal heat sink, put it in the freezer, and that's the source of cold for the supersaturation. And then, Steve, one method used Peltier cooling to actually cool the bottom plate. So the vapor is in there in its foam. It supersaturates because of the Peltier cooling. So you've got much more control in that case. And of course, you can leave it running. A lot of the other methods are very limited in how long they'll run. The gel out of the freezer will only run for half an hour or something like that. Dry ice, you've got to sort of keep it in a dewar or something like that, and it will only run for a short time. But the Peltier cooling method is basically you can run it almost continuously, as far as I can tell. So that just
we've been hammering the ones up at Heathcote are being hammered 24 hours a day.
Yeah, that's right. So
but they're on a heat sink, all right. So
yes.
the object you're trying to cool is there's a sandwich with the Peltier cell in the middle of that sandwich.
Yeah.
The other side of the sandwich is a very large heat sink, and it's a square cross section with a hollow through the middle. That's sort of internal heat sink design with the fins on the inside. And that's designed to have a fan on one end, and we blow the air across the internals of that tube. And the tubes are about 220 millimeters long or so. And the fans are 3,000 RPM, constantly blowing across. And there's all sorts of sensors on the fans. If the fans were ever to stop, then you'll get a thermal runaway. I've measured that phenomena. So there's a shut-off circuit safety mechanism to shut everything down if we have a fan fail. But so far, it's all been designed to work for at least 15 years continuously, but other things cause it to break down. So it has been on and off a while.
Yeah. It sounds similar to this cloud chamber Peltier cooled system, but yes, it does have the advantage. For example, if we were to run public open days at Heathcote or around the state, you could set one of these up with the Peltier cooling, and just leave it running, and the members of the public could come through and see the results. It might be something, Steve, that we talk about along the way, because
Okay.
the ins and outs.
One last thing we could say, Tim, about our surveys that you've spent a fair bit of time on more than myself, is that we've discovered there's an interference that's giving us a bit of grief at 1419 megahertz, 1.419 gigahertz. That's a spike that pops up right in the Doppler range of our receiver bandwidth. And it's annoying. It's always there. That's about minus 300 kilometers per second Doppler.
Yeah, I saw it when you were sharing the screen before, Steve. There was a little sign of it poking up.
But it is obviously, we conclude now that it's something on site up at Heathcote, because it depends on the direction we point the telescope.
Well, it may not be on site, and it could be something off. Well, no, we discussed this. We weren't sure where it's coming from. But it certainly is direction dependent. Yeah.
It's also the nature of it is a narrow band, unmodulated spike. So it's like it's a clock oscillator or something like that. It's not a mobile phone network system, which would be a broad spectrum noise kind of effect. It's WCDMA. So it could be something on our computer system up there, the main computer server, which is in the clubhouse to the southeast of the dish, only 100 meters away or so. It could be something coming from that. Anyway, there's more
go around
more
the
issues
usual thing to turn everything off and then turn them on progressively, or
turning
get a
the server off
antenna.
is problematic, Paul. We wouldn't have remote access then. But being on site and sniffing it out will be the way to go.
Yeah. All right, thank you, Tim and Steve. Excellent progress. I can see Duncan there. Duncan, do you have anything else to add to what's been said, or to your own stuff? Duncan? No, he's gone away again. Well, we'll come back to Duncan if he reappears. IT admin, are you in Australia or US?
I've changed computers since the last time we did this. I'm in Australia right now.
Right.
Unlike Victoria, where you're not getting any rain, up here in Sydney, we've been getting lots and lots of rain.
Yes.
As a result of that, I've been dealing with roofers, trying to, get the roof on our place rebuilt. I'd like to say I was, completing some of my analysis, but that hasn't happened. I seem to be off, doing, rabbit holes and going into places where, it's nothing to do with radio astronomy. And at the same time, I'm getting ready to go to Mauritius, to catch a partial eclipse because we can't get to the Antarctic for the annular, coming up next month. Holiday seasons,
Yes.
you get pulled away everywhere.
I thought you might rise to that challenge, Rob, and head off to Antarctica.
I tried. It didn't work. It's at the wrong part of the Antarctic. It's not close to where the normal cruises go.
Yes.
But we're working on the Antarctic for next year.
Well, plenty of other eclipses for you. Keep chasing them.
Of course. Yeah.
Yes.
Also, making plans for Spain for the August total eclipse.
Oh yes.
Yeah. I have a friend that has accommodation at I think it's on the French Riviera, and I've talked to him trying to get make arrangements to stay at his place for a month. We like to go for a month in Europe and head around to new places.
Yes.
Anyway, nothing really.
Yep. Thanks for that, Rob. Sounds like you've got plenty on battling the rain. You might send some down here, please.
Yeah. I'd like to. Yep.
Yes, it's quite interesting for our US friends, the difference. Some of these weather patterns are extremely localized. Last week we had a massive micro thunderstorm, so micro in the sense of concentrated on a very small area down on the Wye River. So that's southwest of Melbourne, down the Great Ocean Road. If any of you come over, that'll be on your trip list. But that thunderstorm dropped like a year's worth of rain in 5 minutes almost, I think. And the Wye River then flooded, and cars, so it went through the caravan park, cars were swept out to sea. And a week later, it was in the paper yesterday, a helicopter was brought in. They had to close the road and to pull these cars out of the sea. So the insurance companies are going to have a field day down there. And then some of those rain bands have been they've been missing us, but heading up to Sydney and then further north. And then way up in Queensland, they've had massive flooding up there as well. So I would argue all part of climate change. It's the same pattern we've always had, but they're more extreme. We're getting extreme conditions. So moving on, Duncan, are you still there? Try one. Yep. Oh, yep, there he is. Is your audio working today? No.
I heard a chipmunk to start with.
Yeah, there were chipmunks, but no Duncan. No, that's all right. You might have to learn Auslan and do it by sign language. I think that's it for the Australian end. So I'm going to go around on my screen for our US friends, and Dennis, you are the first one on my screen. So.
Okay, thank you, Paul. Can you hear me all right?
Yep, fine.
Great. I'm really enjoying this. I'm not doing much here. Just have an antenna up, but nothing connected right now. As you've probably heard on the news, our Midwest, most of the central part of our country is going to experience a pretty severe cold down in the Dakotas to 50 below, and that's Fahrenheit.
Yeah.
So anyway, I don't know of any snowbirds. You know, those are people that move from the north to the south, from Washington State to Arizona every winter. You get any snowbirds down there?
Certainly people in winter from Melbourne will head into northern New South Wales or into Queensland. Same idea.
Yeah.
Dennis, I'm a skier, and so is Tim, and we love the snow.
Yes.
We don't get enough of it.
I avoid it. Avoid it.
I'm up in northwest Washington, about 90 miles north of Seattle, and we've essentially had a snow drought for several years.
Right.
So there's not a lot of real good skiing here, for at least recently.
Yeah. Well, they're tipping that for here. So Steve and Tim, you better get your skiing in while you can. I think the snowfields are not going to be as effective as they have been. So thanks, Dennis.
Yep.
Thank you.
Thanks for your update. Ted, you're next on my screen. Anything to offer?
I keep poking away on Ezra, trying to add new features. I'm making some progress. And we have different ways to collect data. We started with the RTL SDR, and with brave folks, I'm doing experiments with SOAPy drivers, with indeed the SDR Play, along with AirSpy, and maybe even the B210 from Edis, all kinds of experiments. The same is true even on GNU Radio, a different way to get to different hardware. So new opportunities for data collecting are slowly working their way forward. That's it. Thanks.
Right. Excellent. Sounds like you have plenty on your plate. I watched the comments coming through on the SARA list, and there's a whole load of conversations going on there. Don, you're next on my screen? Anything to offer?
Oh, I have no new thing. I'm waiting for spring. But I think I'm in the same boat as Dennis. We're having a snow drought, and I'm worried about whether I'm going to have to tank in water next summer.
Mm, yeah.
So it may or may not be that way. I have to say, Tim, I'm really impressed by and Steve, your antenna is just doing marvelous job. It's really great. If I gather it right, Tim, you're sort of home brewing your own software for Signal.
Yeah, basically. So I've done two things. One was so I wrote the software for controlling the dish, because what we wanted really was, the original system was just putting the data up onto a screen, and we were driving the dish by hand and then writing down the values by hand, and that's very slow, particularly if you want to do a big scan. So so I worked with Steve and Phil Costigan to get some code running, which is actually on a Raspberry Pi, surprisingly, to both drive the dish and then also pull the data off the software-defined radio, so we could automate the whole thing. And what I've been trying to do is, it's a little awkward, but anyway, is to have that as the graphical user interface, which is what Steve showed, just so that other people can use it fairly simply. So that was written. So I wrote that, and it's now up on the dish software. There's also an analysis thing, which is also written on the Raspberry Pi, and I probably won't be doing much more work on that one. So that's those two things. And then at home, I've got an Apple computer, and I've got a lot of bits of code I've written over the years. I'm a scientist, and I used to work for government labs, and I've got a whole lot of code that I use for processing data. And so I've been just pulling all that in on my desktop here in my unit in my house, and
That's to make the videos and so forth.
and that was to make all the videos and the really
Right.
fancy graphics, because the Apple stuff, they give you all these tools for doing the fancy graphics, where it's a lot harder on the Raspberry Pi. So
Oh yeah.
so that's two things. Yeah.
Do you have a single Raspberry Pi that's not only moving the dish but also taking the data from a B210 or from an SDR play?
The
or...
RSPDX. It's the
Yeah,
RSPDX.
from what I use.
Gotcha. Yeah.
Yeah,
I
Snap,
understand.
Steve.
That's the
Snap.
one. Yeah, sure.
It's not
Yeah.
a bad product. It's what is it? 14-bit resolution.
Yeah, I think it's really good, actually. I'm
It's
quite
not
impressed with
bad.
it.
I have a couple of Plutos that I'm thinking of applying. The what is it? The Pluto from Analog Devices.
Okay. The other thing we
I
could
think
say about the Raspberry Pi, it's a Pi 5.
Yeah, right. Of course. Yeah. Yeah. I've got one of those that I stuck a 2 terabyte drive on the back of. It works quite nicely. It's wound up down at DSES. Okay, well, thank you very much. But I really enjoy your results. They're great.
Yeah.
More to come,
Thanks,
Don.
Don.
And
Yep.
look,
More
if
to come.
anyone's got any suggestions about stuff to scan or to look at, or even in the calibration, that would be useful. Yeah, we're happy to.
Calibration's always a bugger.
Yeah.
If you can, one of the ways that I think they've done it in Germany is to put a small noise source down at the center of the dish that you can turn on and off and use it as a calibration for the feed at any rate. And the other one is to put on the front end oh my God, I'm losing my words. But actually a device to put in a noise source that you can switch on and off.
That's what we do, Don. We've got a a noise reference, which came from radio astronomy supplies.
Right.
And we
Oh, yeah.
switch across to that. We switch across to that, and we get a reference noise.
With a
Yep.
switch, yeah.
Yep.
Yeah, this business, people keep saying a dicky, and that's not really
No.
what you're doing
That's
at
rapid
all.
switching,
That's
though.
not, yeah, that's
usually quite
that's a way to
fast.
that's a way to run a continuous calibration. And
Yep.
it's a completely different thing. And for that,
If we were to do
the
that,
noise,
the relay wouldn't last very long.
no, and besides that, the noise source has to be reasonably close in temperature to the sky that you're looking at.
Yep.
And
yep.
for most of us, that's absolutely impossible.
Yep.
Too hard to do. Anyway, thank you very much. I really like your stuff. It's great.
Thank you, Don. Excellent. Tom, you're next on my screen. Anything further?
No, I will simply apologize for having hit the wrong button. I updated I updated Zoom and it went out, and I really will praise you for the quality of work you're doing. It's nice to follow along, and I have nothing else to contribute.
Right. Thank you, Tom. Gary Steffens, you're next on my screen.
Yes. So actually, this is my first meeting. I recently joined Sarah. I live in Tucson, Arizona, and part of the Tucson Astronomy Club. We just recently formed a radio astronomy special interest group last year, and I'm one of the leads for that. So we're trying to drum up some more interest down here in radio astronomy. I have a scope in a box I've been playing with, and using a laptop for that. I have it attached to an Ioptron Q-Pro mount, so I can steer it around a little bit. I've also tried to use my Raspberry Pi 5, and it generates a tremendous amount of noise, so I had to figure out how to make that behave better. But I'm pretty much new to all this stuff. I did take a radio astronomy class at Swinburne Astronomy Online about 10 years ago.
Oh, good.
So I'm vaguely familiar with a lot of the concepts, but I'm still on the steep learning curve. But I was very impressed with Tim and Steve, the work that you're doing. It's really cool. So
thanks, Gary, and welcome to Drex Lounge Australia.
Thank you.
Hope you're able to join us each time.
Yes.
And Preston, you're the last one on my screen. Fire away.
Okay. I forgot about the meeting, and so I tuned in late. I'm sure I missed a lot of good stuff, but I enjoyed what I heard, and I don't have anything to add. Thank y'all much.
Yep, thank you, Preston. Yeah, we've got to remember time zones, and we're on summertime, which makes the 1 hour difference. But it'll be on the video, so Rich will put it up on YouTube once we're finished. So I think that's everyone. I just had
Paul.
the diary, and yep, sorry, fire away. Someone. You are there.
Yeah, I'm here.
Yeah.
I'm just going to share a screen.
Yep. You were chipmunks earlier on, but you're proper audio now.
Okay, so this is on the left-hand panel. Can you see a dish?
We've got a graph. Pulsar.
You've got a graph.
Velar Pulsar.
Okay, well that's the graph is the Velar Pulsar. That's the update for it. I do Velar observations every day for about an hour on transit, and you can see the pulse period is been going along quite nicely. I'm waiting for a glitch, which is probably due in the next 1 to 2 years. There are some interesting things going on with the observations. Down the bottom left, you can see the dots are pretty quiet, and then I've had a lot of disruption in the timing. I'm going to switch my video off. My connection's just gone unstable. So when you dig into that y-axis on the left, we're getting down to about 10 to the -9 stability in measuring Velar. But I suffer from interference, and there's some speculation now that I'm also suffering from a bit of solar plasma changing the propagation of the device. Anyway, that's about it.
That's quite a dedication, Duncan, if you have to spend an hour every day, and something might happen over the next couple of years.
Yeah, it's looking for things that people don't see. Some people are actually they only do sporadic sampling, which can be a problem. At the top of in the pulse period, you'll see a jump about just before MJD 60,900. That's what happens when the synthesizer unlocks when you don't know about it. You get a jump, but the rest of it, it's the day-to-day stuff. The SNR down the bottom on the Velar is going up and down. It's going up and down for a number of reasons. One, they changed the spectrum allocation in my location, and 8 to 1000 megahertz is pretty crowded with stuff. So I've been having to move around. So at the moment, I found a hole in the spectrum where I actually continue operations, but it's on a slope on the edge of a filter, which means my sensitivity has dropped down from up as high as 40 SNRs down into the 20s. I'm working on fixing that. And I don't know if you can see the dish on the left. Can you see that
It's not
dish?
showing up. No, you might have a split screen or something, do you?
Yeah.
That's one called title.
Yeah. Okay.
Time and
I've got
MJD.
a split screen.
Yeah, I think we're only getting one part of your screen.
What frequency are you using, Duncan, to observe Velar?
It ranges from a band around 8 megahertz, around 820 on, and at the moment 849 and 900. I did have a look locally. There's supposed to be a satellite band at 944, but I put up a high gain Yagi and ended up finding there's a comms links inside the satellite band, so that one wasn't. I wasn't able to use that.
Are we likely to get anything with our dish within the bandwidth of the 1.4 gig range?
Yeah.
Yep.
You've got enough capture area. What do you haven't? So what you need is good clock.
Yep.
I presume. Are you actually using the SDR play SDR input for supplying a frequency reference?
No.
Not yet, but we do have in the laboratory a GPS disciplined time base, which is good to 10 to the -12.
Yep. Well, you need to
we haven't configured that properly yet.
You need to get an output of 24 megahertz into the SDR play, and it has to be there before you turn the device on.
Right.
Otherwise, you have USB problems. You'll get locked out. So, yes, you can do that. The spectral index is dying or declining at 1.4 for Velar. The other news is that the Velar Pulsars actually, well, it's not news, but it's been known for a long time, is located in the Gum Nebula. So there's a high continuum background. It's quite bright there. So it's not the system, it's actually the background of the galaxy that affects it there. So if you're interested, I can send you some GRC code. And I'm sampling this data at around about 3,125 frames a second, so it can actually see the profile of the Velar pulse. So in an hour, you would generate about 2.9 gigabytes. And then there's a whole bunch of analysis software that you can use in that I've written in a script that actually will take the known ephemeris for Velar and run a set of scripts that will actually give you a nice pulse profile out of the data sets. So you can do it at in transit mode. How wide's your beam?
1.4 degrees.
Okay, yeah. So yeah, and you've got the tracking ability, so you can probably track it.
Yeah.
You'll probably find out a lot about your tracking system.
It's the next
when you do
step
it.
I think we want to try and do, Duncan, because we've been neglecting the pulsar studies for the time being. We've just been focusing on neutral hydrogen.
Yeah, I think you've got this data comes off 2.4 meter dish. I might try and stop sharing and I'll try and share the others. I'm going to click on a different one.
So Duncan, you're essentially you average over blocks. You said it was a frame, but I presume you're averaging the power over. I mean, you'd be sampling at quite a high rate, and then you average that, and then that becomes a data frame, like you're averaging over 500 microseconds of data or something.
Yeah, that's okay. So, can you see the image of the dish now?
Yeah, we've got it now.
Okay. So that's a very bashed up 2.4 meter dish with a two linear polarizations. So the data you're seeing on the right, I was displaying before, is actually a data out of one linear polarization. I actually use two because I can beat down the noise if I'm looking for a glitch. The signal paths are only common from the reflector to the antenna. So I have a little bit of discrimination there. Anyway, so you're going back, you're asking what I'm doing. Right, well, at the moment, this data comes 8 megahertz into 128 FFT. And then power detected out of the FFT, squared the I and Q, square it up, get a magnitude, then integrate the frames for about, I think it's 20 FFT frames come out, so I slow it down to give me a data output of about 3,125 frames a second of integrated data. That's then converted to it's all in floating point. It's then short integered and then put out onto a file. So I run the bigger picture is I run a scheduling program, and that starts up the Python script for which is generated by the GRC GNU radio, and that just runs on a clock, which I've got Crony C disciplining my computer, and so it just basically runs unattended as long as the power's not taken away or I run out of memory space. So it's 2.4 meter, and you can do that. I think you can easily do it at 21 centimeters with your capture area.
Yeah.
Yeah. So just one.
Do you have an idea what your T-sys is in continuum?
That's a good question. I'm not sure what you mean.
Well, what's your system temperature? If you've probably got a rough calibration anyway because you're switching in a noise diode.
Tim had a figure on that from some of his recent calibrations.
Yeah, I reckon it's around about 70 Kelvin. That seems to be the background level.
Okay. Does that sound reasonable?
Yeah.
70.
That's reasonable. This thing is probably 75, 80 Kelvin.
Okay.
Most of its noise temperature comes from spill. And it in the LNA. So yeah.
So my one question is, why are you Fourier transforming? What's the, because essentially you just want a time, you're looking at the time signal. So what does the Fourier transform give you?
The Fourier transform gives me the channels so it can adjust for the dispersion of the pulsar.
Oh,
so
okay.
when a pulsar fires a pulse,
Yep.
so the pulse comes out, and as it flies across space from the point of origin, it goes through plasma, and as the pulse gets dispersed in frequency. So its time of arrival is delayed from the upper frequency relative to the lower frequency. So we de-disperse it.
Right, okay. So then you've got to account for that when you reconstruct the pulse.
Yep. Otherwise, it smears itself out.
Okay. Yep. No,
Time of arrival. If you want to see a really bad case of time of arrival, then have a look at some of the plots of the arrival times in frequency of fast radio bursts. You'll see that they really can get delayed a long time, like days.
Oh.
From the upper frequency bands to the bottom frequency bands.
It's like Whistler stuff, isn't it, Tim?
Sounds like it, doesn't it? Yeah.
Yeah, it is whistling.
Like,
dispersion.
Peal of thunder as well in the sound.
Yeah, it's so
frequency.
You can see it on the sun too. You'll see the high frequency start off and then drift in time as it comes down. So that's what you can do.
We need to look into that, Steve, I reckon.
Absolutely, Tim. That's on the agenda.
There's one other
this year. Maybe this year we'll get it.
Yeah,
next month.
there's a couple of comments I made. You probably got enough sensitivity to go down to more pulsars. Velar's quite bright at 4 to 5 Janskis at this frequency, maybe, but it varies. But you've then got to drop to about 200 millijanskis or less to see the next one. And so you've probably got enough to go and actually monitor a few other pulsars that fly through. And there's at least 3 or 4 of them that fly through at minus 40, plus or minus 5 degrees at minus 45 declination. So you can monitor things, and people are interested in this stuff.
Well,
the other thing is, have a look at a survey called the SUM survey, done by University of Sydney. I don't know if it's still on the web, but it does give you an idea of what the background sources are when your beam is passing across the sky, because you're not just getting the continuum sources, you're going to get a number of continuum sources in the beam at the same time. And I think there's one Jansky source for every square degree of that you see in your aperture. So if you work out, you might have quite a few Janskys of noise coming from numbers of sources within the beam. And that's called the confusion limit. You can't resolve between them. So anyway, there are lists of calibrators available, I think, for 21 centimeters out of Parkes in the compact array. That's up the ATCA at Narrabri. So you might like to look at those to see if you could see them. That'll give you a point source in the beam. So that's good for pointing tests, because you can do a thing called Ringo, which is basically you, like you're doing now, but in a ring, point around where you think, halfway down the power, the beam power, whether the sensitivity is high enough for small angular errors, you'll see a large change in the amplitude. You can actually point in a circular pattern around what you think's the center of your pointing center, and you'll see the lopsidedness as you go around it, and they give you an idea what your beam's doing.
Okay, yep.
So it's, plot a ring around it. The other way I used to do even school students can do this one, is you take a parabolic equation, differentiate it once, take some data across, and you really only need 3 or 4 points, but basically way off, but be careful of that. It can make this, what's going to say next, the mathematics blow up. But basically go to the half power points of your beam, central point, go to the half power points, walk it back, take that data, fit it with a parabolic fit. It's a crude way of doing it. And it should tell you your beam offset as a result. If you fit into, you work out that from the differentiation of the quadratic equation. Just fit it in, and it'll tell you how many degrees you offset from the target. If you need more about that, I'm happy to talk, but it's a way of doing it quite quickly. I used to do it professionally, and it was a quick test for where our primary beam was, rather than the actual antenna beam, which was actually much, much smaller and electrically controlled. Yeah, anyway.
Tim and Duncan, have you got one another's email address? And Steve?
I've got Steve somewhere.
Yeah, we've got contact details for Duncan.
Yeah, so
now.
we can. Yep. You can continue the collaboration.
Sure thing. So
happy
Sums,
to do
I'm
that.
just going to copy that link for Sums.
Sounds like you've got some common ground there to explore.
Yeah, the really important thing is when you've got 2 sites and you think you've got a glitch on one site, it's really useful to actually talk to the other site to see if they saw a similar event.
Yeah.
Because there's lots of other things. Gotta go.
Duncan, Ted put in the chat, he's interested in your GNU radio code. So his email is there. I don't know whether you'd seen that in the chat.
No, I haven't. I'll stop sharing.
Yeah. You might want to just take note of that, and a bit more collaboration. That'll keep you busy.
Yep, that's the survey. It's everything from -30 south.
Excellent.
Oh, so just one other question, Duncan, is so do you actually pull out each pulse, or do you have to average over a whole lot of them first?
That's an interesting question, because there's a range of pulse heights coming out of the pulsar. So sometimes they have what they call mega pulses. They're very bright, and I probably could see them individually. But at the moment, I average 20 seconds of data, which is 200.
Right. Yep.
Roughly 220 pulses.
Oh, that's good. No, just to give us a ballpark as to what we need to do to pull out a signal.
Yeah. Faster sampling just gives you more about the characteristics of the pulse, because each pulse out of a pulsar, or pulsars have different pulses, pulse shapes. And I'm about to claim ignorance from then on, because I'm not really a pulsar astronomer.
All right. So sounds like there's some collaboration needed there as well. I'm sure you'll follow that up, and we'll get a reporting back as we go along. Looking in the diary, I've got 28th of February, the Saturday for the Australian end, 27th Friday evening, 27th of February for the US end of things. I'll be in Kangaroo Island in South Australia in that week, and I get back the day before, so I should be okay for that. But all being well. Anything else to chip in before we call it a day? And I'll turn the recording off.
I have one question. Who is Drake, and where is his lounge?
Drake.
Sarah has the get together on Zoom just like this. And one is supposed to be information about your setup, and we kind of get tours, but they all kind of turn into the same thing. of just folks getting together and chatting. That's the current description of Drake's Lounge. Otherwise, in West Virginia, near the Great Big Dishes, there was a kind of place you have coffee or maybe drinks after dinner, and that was the lounge. And Drake revealed his great equation, trying to figure out if there was intelligent life out in space.
Intelligent life. Yep.
It would have to be this division by this division by this division by this division of all those stars out there.
Cool. Thank you.
So Google eventually will find it for you there.
Yeah, it's good. Drake's equation. Drake's equation, very significant.
Yeah, I've heard of that. Yes.
Yeah.
Yeah, and we lost him what, a couple of years ago now, I think.
Yeah, that's right.
He was around until very recently, but sadly no longer with us.
Has anybody seen an article? I saw something on YouTube the other day about the outcome of the SETI experiment, SETI at home, where people relinquished their home computer to do processing for all the SETI measurements that were coming in. And the conclusion is there's about 100 interesting signals that were detected over decades of assessment of this SETI at home program. But a lot of them appear to be natural phenomena, but they're radio signals, but they're a natural phenomena. But they're different, and there's 100 of them, but none of them exhibit communication qualities like a message or something. So, Mr. Drake, there's no life out there yet, as far as we know.
The sample is hideously small.
True.
It is.
Affirmative, and the background drowns it out.
Yeah.
Yeah.
And you
Right.
got the time element as well. You were talking about 13 billion years, and our civilization has only been sending radio signals for 100 and something years. So there's if they're there and we're here, we're not gonna be around at the same time.
Well, we'll have to be sending out our AIs.
Yes. So I'm going to call it to a close. Thank you, everybody, for your contributions. Steve and Tim for the update. Duncan, and we'll hear more in a month's time. Please come and join us, and I'll turn off the recording and say cheerio.
Good
Thanks a
day
lot,
from
Paul.
Montana.
Thank you.